Hi students, please welcome to the Physics Wala. In today's UMEED NEET English batch lecture, we are going to start a very important last but not least chapter, that is Semiconductor Electronics, and you are all familiar with the concepts what we have to learn from this chapter to answer the NEET. But anyway, I will repeat and I will recall the concepts what we have to keep in your mind so that you can answer the questions. So observe this. In today's class, we are going to discuss about the synopsis. Synopsis in the sense important formulas or important concepts or important relations which help us to answer the questions, and later we can move on to the MCQs along with the PYQs, previous year's questions which have been asked in the NEET paper. Okay, so let us start our session without wasting the time. Let us see before going to see what are the semiconductors and all those things, or what are the applications of the semiconductors. Let us have a brief idea about the band theory. Let us have the brief idea about the band theory of the solids. Okay, so observe this. What is a band? What is a band? Or is called energy band. Energy band is nothing but a group of energy levels. Group of energy levels. Available for the free electrons, or for the electrons, we can say. That is the energy band. So what are the different types of energy bands here? Types of energy bands. So just have a look about this energy bands here. So these are all the basic terminologies, the basic things we have to keep in our mind. First one, we have to understand about what is the valency band. Valency band is nothing but the band which consists of energy levels of free electrons. Okay, or we can say the group of energy levels for the valency electrons, we can say. So please observe this. Is the, you can say, it is a filled energy band. Filled energy band is nothing but the group of energy levels filled with electrons, free electrons. Okay, filled energy band, because on energy levels in this point or in this band, energy levels are occupied by the free electrons or the valency electrons. We have to think here. And later we have to go with the second energy band, that is, we can say conduction band here. Conduction band, we can say it is an empty band. Because the energy levels are always in the always seeking the free electrons, or we can say that the band or the group of energy levels which are empty. Okay, or the group of energy always have a tendency to have the free electrons. That is a conduction band. We can say it is an empty band. Only few electrons, or we can say they are partially filled with the electrons. Partially filled with the electrons, we can say. Partially filled with the electrons, and later we can say that the electrons which are present, electrons in the conduction band are responsible for, the reason for conductivity. They are the reason for conductivity or conduction of both heat as well as electric current. Okay, and later we have to understand about what is the energy gap. Energy gap is nothing but the difference in the energy between the valency band and conduction band. Valency band and conduction band, okay, is called, we can say that energy gap, usually denoted by Eg. So based on this energy gap, okay, solids are classified, broadly classified into three types, So that is classification of solids, we can say classification of solids. So we think on how can we analyze this point here, classification of solids. First one we have to think about insulators. Insulators here. What are the insulators? Just I will show through diagram. Please observe this. Whenever we consider the conduction band is nothing but higher energy band, and there is a valency band which is filled band, and if the conduction band and valency band are separated by an energy gap greater than 3 electron volts, then the solids are referred as insulators. Okay. And second one, whenever we move on to the conductors, we can say that observe this, the conduction band and valency band, okay, are overlapped with each other. If the conduction band and valency band overlap each other such that energy gap is taken to be equal to 0 electron volt, then they are referred as conductors. Okay, and later we can move on to the semiconductors, okay, on which we have to concentrate more, semiconductors. So please observe this. What are the semiconductors? If the conduction band and the valency band are separated by small energy gap. Please remember these values also here. It is less than 3 electron volts. If the conduction band and valency band is separated by a small energy gap which is less than 3 electron volt, then those solids are referred as what is the semiconductors. Okay, now observe this. Semiconductors, we can say that the conductivity of insulators will be less than conductivity of the insulator is less than the conductivity of the semiconductors is less than the conductivity of we can say conductors, or we can say that resistivity of the insulator is greater than the resistivity of semiconductors greater than the resistivity of conductors. And simple case we can say the substances or the solids or the materials whose conductivity or resistivity lie between insulators and conductors are referred as semiconductors. Is it clear? I hope you understood this point here. At room temperature, only few electrons can jump from valency band to conduction band in semiconductors, giving rise to partial conductivity or partial resistivity or partial conductivity. Okay, and please observe this. As the temperature increases, we can say conductivity of the semiconductors also increases, and resistivity. What can you say about the resistivity of the semiconductors here? Resistivity of the semiconductor will decrease. Because of this reason, semiconductors are said to have negative temperature coefficient. I am repeating, semiconductors are said to have the negative temperature coefficient. What is the meaning of that? As the temperature of the semiconductor increases, the conductivity will increase or resistivity will decrease. We have to remember, and later we have to understand. Observe this. At 0 Kelvin, what is the 0 Kelvin? That is minus 273.15 degree Celsius. We can say semiconductors semiconductors will behave like a will behave semiconductors will behave like a perfect insulator here. Perfect insulator. Semiconductors will behave like a perfect insulator. Perfect insulator. Okay. I hope you understood this basic points about the semiconductors. About semiconductors. Okay. And whenever we move on to the types of semiconductors, here types of semiconductors. Types of semiconductors. Okay, before going to see the semiconductors types, let us have what are the examples? What are the examples of semiconductors? Please observe this. What are the examples of semiconductors? Please make a note of this. We can say that in elemental form, the best example is germanium and silicon. Germanium and silicon are called as elemental form of pure semiconductors. Okay, and in inorganic form, in inorganic, we can say that we can go with gallium arsenide, and in organic we can take an example of anthracene. Anthracene is an example of semiconductor. That means at room temperature the materials and the solids okay, which show partial conductivity at room temperatures are referred as semiconductors. Okay, now let us move on to the types of semiconductor. Here types of semiconductor. Okay, so let us have the first one, that is intrinsic semiconductor. Here we can call it as the first one, intrinsic semiconductor. So what are these intrinsic semiconductors? How can we understand about this intrinsic semiconductor? Means let us go with the first point. We can say pure form. Whenever we take the pure form of semiconductor, then it is referred as intrinsic semiconductor. Example, germanium and silicon. Okay, so please observe this. And in intrinsic semiconductors, we can say that number of electron concentration is equal to number of hole concentration. What is Ne or NH? Here Ne or NH represents number of electrons are holes, per unit volume, or simply we can also call it as concentration, electron concentration or hole concentration. We have to think. So later we have to understand about the conductivity of intrinsic semiconductor is due to both electrons and holes. What are these holes? I will explain to you, no need to worry. Okay, electrons and holes, the conduction of the semiconductor will take place because of electrons and holes. So please observe this. Conductivity is written as we can say that Ne into mu E plus NH into E into mu H, we can write. This is the expression for calculation of conductivity of a semiconductor. What is this What is Ne here? Ne, we can say electron concentration. NH, we can say hole concentration. But what is this mu E? Mu E is called as mobility of the electrons, and mu H are called as is called as mobility of the holes, And please remember that how can we define mobility here? Mobility is defined as drift speed per unit electric field. Okay, so based on this formula also we can expect the questions on semiconductor. So one thing you should be very clear that and be confident, maximum to maximum the questions asked from the semiconductors are all in the form of theory, in the form of theory. But rarely they can ask the questions based on these formulas, based on these formulas. Okay. I hope it is clear to you. That is about the intrinsic semiconductor here. And one more point we have to understand that conductivity of pure semiconductor or intrinsic semiconductor is low. Is it clear? And one more thing, please observe this. In conductivity or in pure form of semiconductor, in intrinsic semiconductor, there will be an energy level. There will be energy level between the valency band and conduction band, and we call that energy level as a Fermi energy level. So observe this. Fermi energy level is denoted by EF. What is this Fermi energy level? Is nothing but the energy level related to impurities. Okay. And the Fermi energy level related to impurities are referred as the Fermi energy level. And in intrinsic semiconductor, the Fermi level are Fermi energy level lies exactly in the midpoint, between or middle between the conduction band and valency band. Okay, that is about the intrinsic semiconductor. Here, intrinsic semiconductor. Later, we have to understand about extrinsic semiconductor. Extrinsic semiconductor. Okay. So what is the extrinsic semiconductors? How can we define this? Observe this. When impurities are added to pure germanium, intrinsic semiconductor, that is pure germanium or silicon, we get extrinsic semiconductor. Here we get extrinsic semiconductor. Okay, when impurities are added for pure, what is a pure semiconductor like germanium or silicon, we get the extrinsic semiconductor. Okay, so observe this. What are the points we have to understand under the extrinsic semiconductor here? One thing we have to very clear that conductivity is high compared to intrinsic semiconductor. Conductivity will be high for impure or extrinsic semiconductors. And one more thing we have to understand that number of electron concentration is not equals to number of hole concentration. That is, number of electrons is not equal to number of holes. Okay, that is about the intrinsic semiconductor here. Later we have to understand what is the meaning of doping. What is the meaning of a doping? Doping in the sense the process of addition of impurity. The process of addition of impurities is called process of addition of impurities is called doping. As a doping. And what are the dopants here? What are the dopants? Dopants are nothing but the impurities added here. Impurities added to the pure semiconductors are called as dopants. Okay, and later we have to understand what is the meaning of a hole. So please observe this. How can we understand the meaning of a hole? So please look at the board here. And we know that in a solid there will be conduction band and there will be valency band. Is it clear? In valency band there will be filled electrons, or all the energy levels are completely filled with the electrons, we can say. So please observe this. And at room temperature, if the electron jumps from valency band to conduction band, then there will be a hole, vacancy, there will be a gap created in the valency band, and that gap is called as a hole. That gap is called as a hole. So what is a hole here? Hole is nothing but nothing but vacancy. Vacancy created in the absence of electron, in the absence of electron, in the absence of electron in valency band, okay, is called hole, is called as a hole. Or the vacancy, yeah, due to excitation of electron from the valency band to conduction band is referred as hole, is referred as a hole, okay. And please observe this: hole is a positively charged carrier. Here hole is a positively charged carrier. Hole is a positively charged carrier. And we can say that one more point, that is conductivity of a hole, conductivity of a hole is less compared to that of electron, compared to that of electron, we can say. So whenever we compare the conductivity, of a hole with respect to electron, its conductivity is less. Less. These are the important points what we have to keep in our hole. And where the hole will lie? Hole will lie only in the valency band. Okay. So in valency band, since there are a large number of electrons, we can say mobility of a hole is less compared to the electrons, compared to that of electrons. Okay. Now later we have to understand about what are different types of extrinsic semiconductor. Here different types of extrinsic semiconductors. Okay, there are two different types of extrinsic semiconductors. Very easy topics, because most of the concepts has been deleted. For example, we can say transistors. So transistors are completely related, which occupies the major part of the semiconductor electronics. Okay, we have to learn only about the introduction of the semiconductors, classification of the semiconductors, and application of semiconductors. Okay, and if possible, I will explain the Zener diode. Zener diode is not there in the syllabus, but anyway, I will explain the basic formulas and logic gates. Actually, logic gates are also not included in our NCERT book, but anyway, I will explain so that we can learn. There are different types of semiconductors. In the first one, p-type semiconductors. Here p-type semiconductors. Okay, so how can we get the p-type semiconductors? We can say here. So please observe this: when germanium or silicon are added with trivalent impurities, okay, then we will get the p-type semiconductor. Okay, example for trivalent impurities. The best example is indium, aluminum, boron, okay, etc. These are all the best examples of we can say trivalent impurities. What are trivalent impurities? The atoms are the elements which has three valency electrons, or the three electrons in the outermost orbit. Are referred as trivalent impurities. Okay, and in p-type semiconductors, we can say that number of holes will be greater than the number of electrons. Number of holes is greater than number of electrons. And one more thing, and since number of holes is greater than the number of electrons, we can say that what can you say about this conductivity here? Conductivity of p-type semiconductor. P-type is low, because holes has low conductivity property. Because of the reason, p-type will also have the low conductivity. Okay, and observe this: these impurities which are added to the pure semiconductors like germanium or silicon, okay, are called as are called as acceptor impurities. Here acceptor impurities are called as acceptor impurities. Okay, and as I said, for the impurity atoms, there will be an energy level called Fermi energy level. And for p-type semiconductor, this Fermi energy level will lie close to the valency band, close to the valency band, because they are called acceptor. That means they are ready to accept the free electrons. And where those free electrons will exist? Those free electrons will exist in valency band. Is it clear? Therefore, the Fermi energy level, okay, will lie very close to the valency band, and this Fermi energy level is referred as the acceptor impurity level, or simply we can say acceptor level. Okay, that is about the p-type semiconductor. Okay, and later we have to understand about the second one, that is n-type semiconductor. So please observe this. P stands for positive type semiconductor. Why the name has given p type? In the sense, since holes are majority charge carriers, the name is given as positive type semiconductors. But it does not mean that they are positive type semiconductor. Okay, positive type semiconductor is different. Sorry, they are not positive semiconductors. Positive semiconductor is different from positive type semiconductors. Okay, so please have a look here about the n-type semiconductor here. And when pentavalent impurities are added, added to pure silicon or germanium, we get what is it? N-type semiconductor. Okay, what are examples of this n-type semiconductors here? Examples we can say, the best example is arsenic, phosphorus, okay, we can bismuth. These are all examples of n-type semiconductors. And in n-type semiconductors, we can say number of electrons or whole electron concentration will be greater than the whole concentration here, will greater than whole concentration. And one more point we have to write here. And what is the conductivity here? So how can I the conductivity? Conductivity is equals to NH into E into mu H. NH into E into mu H. Okay. And similarly, what is the conductivity? Conductivity will be equals to conductivity of n-type semiconductor is equals to Ne into E into mu E. Ne into E into mu E. And one more thing we have to understand, that conductivity will is high for n-type semiconductor. For n-type semiconductors, conductivity will be high compared to p-type semiconductors. Okay, and these pentavalent impurities which are added, are referred as donor impurities, because these impurities are always have a tendency to donate the electrons. Okay, therefore the impurity energy level, that is Fermi energy level, will lie close to the conduction band. See, observe this. The Fermi level will lie very close to the conduction band, because these impurities always have a tendency to give electrons. Which band will require electrons for conduction? Only conduction band. Okay. Therefore, this energy level or this Fermi level will be very close to the conduction band, and we can call this energy level as a donor level. Okay, I hope you understood these points clearly related to p-type semiconductors and n-type semiconductor. Okay, later we have to understand. Later we have to understand about what is the p-n junction here. p-n junction. p-n junction diode. p-n junction diode. Okay. So please make sure you are understanding each and every point. p-n junction diode. Okay. So how can we understand formation of p-n junction diode and what happens during the formation of p-n junction diode? All those points are very, very important. So many people think that p-n diode is formed. p-n diode is formed by joining p-type semiconductors and n-type semiconductors back to back. But that is not the exact way of forming p-n diode. So observe this. Whenever we consider the pure germanium or silicon, observe this. And at one end, we add p-type impurities. Impurities. At one end we add p-type impurities, and at the other end we will add n-type impurities. So that we can say that in p-type, in this region or one end of the semiconductor, there will be holes or majority charge carriers. Holes will become majority charge carriers. On the other end, the electrons will become majority charge carriers. At one end, where we add p-type impurities, holes become majority charge carriers, and to the other end where we add n-type impurities will become electrons will become majority charge carriers. So please observe this. Due to, first one we have to understand that due to charge difference here, due to charge difference or potential difference, holes and electrons, diffuse from p type to n type. Holes will diffuse from p type to n type, and electrons will diffuse from n type to p type, okay. So that is about what happens during the formation of p-n junction diode, okay. And after some time, whenever the diode or junction is formed, this is the p region and this is the n region. Please have a look carefully. Near the p region, there will be an immobile layer of holes, and near the n region, near the n region at the junction, okay, there is an immobile positive layer, and near the p region, there is an immobile negative layer, okay. And observe this. Because of this formation of the immobile layer, there will be some potential difference, and we can call this potential difference as a barrier potential, okay. And please look at the board carefully. And near the junction, observe my words, listen my words carefully. Near the junction, electric field is directed from n region to p region. At the junction, I am repeating the sentence, at the junction, electric field is directed from n region to p region. So please look at the board here. If D represents width of the junction, if D represents the width of the junction, VB represents the potential barrier, VB represents the potential barrier, and capital E is the electric field intensity, electric field at the junction. Then we can say that the junction field is equals to potential barrier divided by width of the barrier. E is equals to VB by D. Okay, so that is about the formation of this here. Look at the board carefully. Okay, so observe this. The current due to majority charge carriers, here the current due to majority charge carriers is called diffusion current, is called as diffusion current. Okay, and later we have to understand the current due to minority charge carriers, is called drift current, is called as a drift current. Okay, I hope you understanding each and every point here. Minority charge carriers, observe this. For example, electrons are minority charge carriers in the p region, and holes are minority charge carriers in the n region. P will move towards the n, and electron will move from p region to n region, and hole will move from n region to p region. Okay, so these are the points what we have to understand here. And one more thing, observe this. The region at the junction which are free from the charge carriers. Okay, I will write this. The region at the junction the region at the junction which are free from charge carriers, is called depletion region, is called as a depletion region. Okay, so like that we have to understand the important points related to the formation of PN junction. Now let us move on to the next concept, that is biasing. What is the meaning of biasing? So please observe this. Biasing is nothing but the external DC supply, or we can say that whenever the DC supply is connected to a diode, that process. So see here, the process of applying the DC supply for a diode is called as the biasing, and there are different types of biasing here. First one, we have to understand forward bias. How can you understand the meaning of this forward bias? Please look at the board here. And whenever we consider p type is connected to positive terminal and n type is connected to negative terminal, then the diode is said to be forward bias. In forward bias, what are the points we have to understand? Observe this. In forward bias condition, width of the junction will decrease. We can say. And later, please observe this. Diffusion current will be greater than drift current here. That means the current due to majority charge carriers will be greater than the current due to minority charge carrier, because whenever the width of the junction width of the junction decreases, we can say maximum number of majority charge carriers can easily move from P region to N region in a region. Okay, so because of the reason, we can say diffusion current will be greater than drift current, current. Okay, and one more thing we have to understand that potential barrier, potential barrier will decrease, we can say. Okay, and later we can move on to the we can move on to the next one. Please observe this. The forward bias resistance here. The forward bias resistance will decrease, will be nearly 10 ohm to 25 ohm for a practical diode, okay. And later we have to understand for an ideal diode, we can say that forward bias resistance here, we can say forward bias resistance will be equal to 0, okay. Forward resistance will be equal to 0 in case of an ideal diode, okay. Later we have to understand, so please observe this. So N should be connected to negative in the sense low potential, okay, and P should be connected to positive in the sense high potential, then only it is said to be in forward bias condition, So whenever we observe the voltage, or whenever we observe the potential barrier, please look at the board. This is the P region and this is the N region, we can say. So please have a look here, and this is the normal, this is unbiased way. In this unbiased condition, we can say that there will be a potential barrier VB, we can represent there will be a potential barrier. But in forward bias condition, the barrier potential will get decreased. We can say barrier potential will get decrease. Okay, so that is about the point we have to keep in our mind. Okay, so later we can move on to the next, that is the reverse bias condition here. Okay, in forward bias condition, what is the graph? IV graph. What is the IV graph or VI graph? So please look at the board here. Whenever we consider the applied potential along the x-axis and the current along the y-axis, the graph is as shown in the figure. Please look at the board. The graph, observe the graph carefully, and the voltage and the applied voltage at which the current increases rapidly or current increases gradually is called as knee voltage, What is the knee voltage? We can say here it is a voltage applied to the forward bias or applied to a PN junction diode in forward bias condition, at which the current gradually increases. That is called as a knee voltage. Okay, and later we have to understand. About what is the second one. That is a reverse bias condition here. Reverse bias. Okay, I will write in complete words. Reverse bias. So how can we define this reverse bias here? So please observe this. Whenever we consider the p-type region of a semiconductor is connected to negative terminal, and n-type region of a semiconductor is connected to a positive terminal, then the diode is said to be in reverse bias condition. Okay, and in reverse bias condition, the width of the barrier will increase here. The width of the potential barrier will increase. Width of the potential barrier will increase. One more thing, we can width of the junction or width of the barrier, or we can say that barrier potential also increases here. barrier potential barrier potential also increases. Barrier potential also increases. Okay, better we can say, say, so please observe this. Width of the junction, width of the junction will increase. Width of the junction will increase. Barrier potential also increases. And one more point we have to understand, that diffusion current will be less than the drift current. Diffusion current will be less than the drift current. Later, we have to understand about the resistance of the diode in reverse bias condition. Here, resistance. What can you say about the resistance of a diode? Here, resistance of a diode in reverse bias, is approximately, we can say that 10 to the power of 4 to 10 to the power of 5 ohm, 10 to the power of 4 to 10 to the power of 5 ohm. But for an ideal diode, we can say that the resistance will be infinity. In case of ideal diode. So please observe this. Whenever there is an ideal diode in the circuit, in forward bias condition, it will conduct the current through it. And whenever there is a diode in reverse bias condition in the circuit, in that branch, no current will flow. Okay. So like that we have to understand here. And later, whenever we observe the graph, observe this. This is a P region and this is a N region. And in unbiased condition, let us say the potential barrier is as shown in figure. Okay. And suppose whenever it is in reverse bias condition, the potential barrier will be greater than the thing here. So this is the potential barrier in case of reverse bias condition. Okay. Later we have to understand about the IV graph, or VI graph. So observe this. And whenever the diode is in reverse bias condition, we will apply the negative voltage. So please observe this. This is the applied voltage and this is the reverse current. And when you plot the graph, the graph is as shown like this. Okay, at one particular voltage, what can you say here? The current grows, the current rapidly increases, and that particular voltage, reverse voltage applied to the diode, is called as a breakdown voltage. Here is called as a breakdown voltage, or Zener voltage, a Zener breakdown, or a breakdown voltage. Okay, I hope this is the reverse bias characteristics. And later, please observe this. We can say that PN diode is used as a okay, one of the applications. What the applications of this PN junction diode means? That is rectification. Here, rectification. Observe this. What is the meaning of rectification here? Rectification is nothing but the process of conversion of AC to DC. The process of conversion of AC voltage to DC voltage is called as a rectification. And the device used to convert AC to DC is called what is this? Rectifier. Is called as a rectifier. Okay, so please have a look here. And there are two types of rectifiers here. One is called as a half wave rectifier. Okay, so please observe this. Half wave rectifier. Okay, so can we understand this half wave rectifier here? Half wave rectifier, please observe this. And whenever we consider the circuit, the circuit consists of a transformer. Circuit consists of a transformer, and along with one diode. This is the point A, and this is the point B. B. So please have a look here. And across the diode, there will be a load resistor. There will be a load resistance, and across this load resistance, we can measure the output voltage. We can say this is a transformer. Okay, please have a look here. What this half wave rectifier will do means it converts only positive half cycles here. Positive half cycles of an AC to DC, we can say. So please observe this. Whenever we observe the input and output waveforms from here, observe this. In this V input, input the positive half cycle and negative half cycle, there will be like this, positive, negative, positive, like this. And whenever we move on to the output voltage, so there will be only positive half cycle. There will be only positive half cycles here. Positive half cycles will get converted into DC. That means negative half cycles cannot be converted into DC with the help of half wave rectifier. Okay, so what is the efficiency of this half wave rectifier? How can we write this efficiency? Please look at the board here. Efficiency of a half wave rectifier is equals to 0. It should be 40.6 40.6 into RL divided by RL plus we can say RF. What is this RL here? Where capital RL is a load resistance, is called as a load resistance, and RF is the forward bias resistance of a diode, we can say, and we can say maximum efficiency of half wave rectifier is only equal to 40.6% here. 40.6%, that is a maximum possible efficiency of a half wave rectifier. Okay, later we have to understand about what is the full wave rectifier. Okay, what is this full wave rectifier here? The device or the circuit which converts both the half cycles here, both half cycles of an AC to DC is called half wave rectifier. So please observe this. In full wave rectifier, there will be a transformer. Which is center tapped, along with there will be two diodes. Please observe this. These are the two diodes we can say. Please look at the board carefully. These are the two. There is a D1 and this is a D2, and there is a center tap connection. And with the center tap connection, there will be a connection of load resistance across which we can measure the output voltage. Okay, V in is the input voltage. Why the center tap is used? Why the center tap connection is used? So say here, because of the center tap connection, we can say the diodes will change the potential, their potential periodically with respect to input waveform. Okay, the center tap connection changes the potential of these two diodes with respect to input waveform. Okay, so please have a look here. What is the efficiency? efficiency of a full wave rectifier is equals to 81.2 into RL divided by RL plus we can say RF. So maximum possible efficiency of a full wave rectifier. What is the maximum possible efficiency? Maximum possible efficiency eta is equals to 81.2%. 81.2%, that is the maximum possible efficiency of a full wave rectifier. Full wave rectifier. Okay. And whenever we draw input and output waveforms, here input and output waveforms, please have a look here. This is the input waveform. In input there will be both positive half cycle and negative half cycle. Whenever we plot the output waveform, we will get only positive half cycles, only positive half cycles of an AC, positive half cycles of an AC. Okay. So like that we have to think and we have to analyze about the full wave rectifier, Okay. Later we can move on to the what are the applications of the PN diode. And see here, PN diodes can be used as LEDs, that is electronic photo electronic devices. LED, light emitting diode, which is not there in the syllabus, so no need to worry about that. And solar cell, and also we can say photodiodes. Okay. So let us understand about what is the Zener diode. Here, what is a Zener diode? What is Zener diode here? And we have learned that previously. Whenever a PN junction diode is used in the reverse bias condition, it do not conduct the current. Okay. So therefore, in order to conduct the current in reverse bias condition, is a diode is designed, and it is referred as a Zener diode. So what kinds of Zener diode here? We can say that a heavily doped PN junction diode, heavily doped PN junction diode. Okay. So please have a look here. Heavily doped PN junction diode, heavily doped PN junction diode, which is used to in reverse bias condition. Is it clear? Therefore, see here, a heavily doped PN junction diode, which is used to operate in reverse bias condition. Reverse bias condition is called as a Zener diode. Heavily doped PN junction diode used to operate in reverse bias condition. Okay. That is called as Zener diode. And what is the circuit symbol here? What is the circuit symbol? Circuit symbol is as shown in the figure. Please have a look here. This is a circuit symbol. This is a P and this is the N. Okay. That is a Zener diode. One of the application, but anyway, it is not there in the syllabus. So just have an idea. About this Zener diode. So please observe this Zener diode as a voltage regulator. Voltage regulator. Please have a look here. What is a circuit diagram? Related to this voltage regulator? Here, please look at the board. There will be one series resistance. Along with there will be a Zener diode as shown in the figure. So please observe this. This is the Zener diode. Across the Zener diode, there will be a load resistance. So across the load resistance, we will measure the output voltage. And here we will give you the input voltage. So let's say if I is the main current, if I is the main current flowing through the circuit at this junction, it will get splitted into two parts. Here one is IL and the other one is IZ. Therefore, first point we have to understand that the main current I can be written as IL plus IZ. There is a load current plus Zener current. Okay. And second one, please observe this. Input voltage applied is equals to voltage across the load series resistance plus voltage across the Zener diode. So please look at the board carefully. V input can be written as I into Rs according to Ohm's law. Voltage across the Rs is equals to I into Rs plus what is the voltage across the Zener diode here? Voltage across Zener diode can be written as Iz into Vz, otherwise IL into RL, because voltage across the Zener diode is nothing but what is that? Output voltage. Okay, this is the important equations we have to keep in our mind to answer the questions related to voltage regulator, Zener diode as a voltage regulator. So if you remember these formulas and apply it in a proper way, then definitely you will get a correct answer related to this particular questions. Okay, now later we can move on to the logic gates. What are these logic gates? So what are these logic gates here? Logic gates are nothing but the circuits which operates the circuits which operates between two logic values or two logic levels. So two logic levels 0 and 1. 0 and 1 here. Two logic levels 0 and 1. Okay, I hope you understood this. And there are different types of logic gates. See, observe this. Logic gates are nothing but digital circuits which are used to operate between two logical values 0 and 1. Usually 0 stands for low, false, no, off states, and 1 stands for high, true, on states. Okay, that is about the logic gate. That is about the logic gates, circuits which operate between two logic levels. And there are different types of logic gates. Among them, the first one we have to understand about what is the AND gate. We have to understand about the AND gate. So please have a look here. AND gate. What is circuit symbol? It will appear as a D shape. And this logic gates at this present level, that is at the 12th standard level, there will be only two input and one output. So observe this. A and B are called as inputs. A and B are called as inputs, and Y is called as output. Y can be written as A dot B, and we have to read it as A and B. That is a circuit symbol, and this we can say it is a Boolean equation here. Boolean equation which is used to represent AND gate. Okay. Later we can move on to the truth table. Okay. So please observe this truth table. So whenever we consider the things here, truth table. What is truth table? Truth table is nothing but the tabular column used to represent both inputs and outputs, possible inputs and possible outputs of a circuit. This is A and this is B and this is Y. That is A dot B. Please have a look here. 0, 0. But if both the inputs are low, output is also low. See here 0, 1, then also output will be low. 1 0 output will be low, 1 1 output will be high. So how can we define this AND gate here? How can we define this AND gate? AND gate is defined as we can say that the logic circuit whose output is high if and only if both the inputs are high. That is about the AND gate. Okay, I hope it is clear my here. AND gate is the circuit symbol, equation, and the truth table. Okay, later we can move on to the second one, that is the OR gate. We can go to the OR gate. So please observe this R. How can we represent or how can we identify the OR gate? Please have a look. This is the circuit symbol of the OR gate. There are two inputs here, A and B, and there will be only one output, and which can be written as A plus B, and we have to read this as A or B. So what is the truth table here? Truth table. So please have a look here, truth table. Whenever we consider the two inputs and one output here is A, B, and Y is equals to A plus B. So please have a look here. 0 0 output is 0. 0 1 output is 1. 1 0 output is 1. 1 1 output is 1. That means how can we define this OR gate here? OR gate can be defined as the logic circuit whose output is high if any one of the inputs are high. That is about the OR gate. Okay, and third one we can say that is a NOT gate. Here we can say it is a NOT gate. What is NOT gate here? Please look here. Whenever we consider the symbol, a NOT gate consists of only one input and one output. So NOT gate is defined as the logic circuit whose output is the complement of input. So what the truth table we can say? So for a NOT gate, there will be only two possible things. One is input and one is output. If A is 0, if A is low, Y is high. If A is 1, Y is 0. That is about the NOT gate. Later we can move on to the fourth one, that is NAND gate. Here NAND gate. So please look at the board here, NAND gate. How can you understand about the NAND gate? Please look at the board. So this is an AND gate followed by a NOT gate. Please, this is A and this is B, and this will be the output Y. Y is equals to A dot B whole complement. Or we can also write this NAND gate as shown in the figure. We'll write and if we write the bubble at the end, this represents the NAND gate. A dot B whole complement is A and this is B. So what is the truth table we can say? Please have a look here. Truth table, this is A, this is B, and this Y is equals to A dot B whole complement. Okay, so please observe this. This 0 and this 0. So A and B, it will become 0. 0 complement becomes 1. If I say 1 0, 1 dot 0 is again 0. 0 complement is 1. So 0 1 again 1, again 1 1, it becomes 1. 1 complement is 0. Okay, that is how we can define NAND gate, exactly opposite to AND gate. Now let us move on to the next gate, that is called as NOR gate. Please observe this. What is NOR gate here? Observe this. This is the OR gate followed by the NOT gate followed by the NOT gate. Please have a look here. There will be two inputs A and B, and output can be written as A plus B whole complement, A plus B whole complement. Okay, so please have a look here. NOR gate can also be represented by writing a bubble at its end. This is A and this is B. Output will become equals to A plus B whole complement, A plus B whole complement. And whenever we write the truth table will be as shown in the figure. It is exactly opposite to OR gate, exactly opposite to OR gate. So please observe this. A plus B whole come 0, 0. Actually, OR gate will give output 0. But 0 complement will become 1. So 1 comma 0, 1 comma 0 will give 1. So 0, 0, 1, 0, 1, 1 is also equal to 0. Okay. So like this, we have to analyze about the NOR gate. Later, we have to understand an important point, that is, see, look at the board, and OR gates, and OR gates are called basic gates, are called as basic gates. Okay, and second one we can say, that is, observe this, NAND gate, NAND and NOR gates, are called as we can say, that is, universal gates. We can call it as universal gates. Okay, and please have a look here. What is the Boolean De Morgan's theorem? We have to understand about De Morgan's theorem. De Morgan's theorem. So how can we understand about De Morgan's theorem here? Please observe this first one. Observe this. Y is equals to A plus B whole complement, A plus B whole complement, or we can say A plus B. That is the complement of sum of the two variables is always be equals to the product of individual complement, the product of the complements of individual variables. And similarly, if I write A dot B whole complement, then A complement plus B complement, A complement plus B complement. Okay, that is the De Morgan's theorem. De Morgan's theorem. I hope you understood this point clearly. Is it clear? And there is one more gate. If you want, I can explain. That is XOR gate, exclusive OR gate. We can call it as exclusive OR gate. Please look at the board here. Exclusive OR gate is as shown in the figure. Please have a look. This is the A. This is the input A, and this is also input B. So what can you say about the output here? Output can be written as A complement B plus A B complement, A B complement. This is the Boolean equation, which is used to represent the output of exclusive OR gate, that is XOR gate. Okay, I hope you understood these points clearly to everyone. Okay, now let us start. Start answering the questions, from this particular chapter, Semiconductor Electronics, which are given in various state entrance examinations, and also in the previous years pre-medical entrance examinations. Okay, so before going to answer the questions from this particular chapter, I request everyone to learn these formulas, and to learn or to understand these concepts carefully, and practice the formulas as many times as possible. Okay, I hope you will do this here. Let us see the first question, what they have given to us and how to answer this question. Please observe this. Identify the wrong statement. These are all the questions which are given in the previous years pre-medical entrance examinations of various states which includes NEET also. Please observe this. In conductor, the valency band and conduction bands overlap. It is correct only. No, it is correct. So substances with energy gap of the order of 10 electron volt are insulators. If the energy gap is greater than 3 electron volts, then only they are called as insulators. So says here, the resistivity of semiconductors is lower than metals. Okay. I hope it is clear to you here. The conductivity of the metals is high, and the resistivity of semiconductors is lower than that of insulators. Okay. So which of the statement is wrong? Whenever we observe the options, we can say we have to select the wrong statement. We can know that the conductivity of metals is high and the resistivity of semiconductor is lower than that of insulators. But whenever we come across the resistivity of semiconductor is lower than that of metal, that is a wrong statement, because the resistivity is less than that of metals. Sorry, is greater than the metal, because conductivity of the metals is greater than the conductivity of semiconductors, greater than the conductivity of insulators. Okay, hence we can select option C as the right answer. Move on to the next one. Based on the band theory of conductors, insulators and semiconductors, the forbidden gap is smallest. Smallest in forbidden gap. Insulator we can say Eg is equals to 0. Conductors is equal to 0. Insulator is greater than 3 electron volts. Semiconductors, it is less than 3 electron volts. Okay. Hence we can go with option A as the right answer. If you learn all these questions, definitely you can answer any question from your NEET entrance examination. Okay. So observe this. For an insulator, the forbidden energy gap is, forbidden energy gap should be greater than 3 electron volts. Hence we can select 5 electron volts. Is it clear? So that is the option here. So move on to the next one. Forbidden gap in the energy bands of silicon. They are asking what is the energy gap in the silicon here. So whenever we move on to the silicon, what is silicon here? Silicon is an example of semiconductor, and therefore we can say silicon will have the energy gap, it is equals to 1.1 electron volt here. Energy gap will be equals to 1.1 electron volt. And similarly, whenever we want to the germanium, for germanium we have to think energy gap will be equals to 0.7 electron volt, and these are all the standard values you must remember. Okay. So like that we can move on to the next question. What they are saying to us. The forbidden energy gap in the germanium is 0.72 electron volt. Given that Hc is equals to 12,400 electron volt angstrom, they have given the maximum wavelength of the radiation that will generate electron hole pair. Okay, they have to find out what is the wavelength. We have studied in the previous chapters like dual nature of radiation and matter and atoms. We have studied that lambda is equals to 12400 divided by Eg. Definitely electron energy should be electron volt, then lambda you will get directly in angstrom, so please observe this. 12400 divided by 0.72. So whenever we do calculation, you will get approximately, it should be greater than this 12,400 here, greater than 12,400 in the sense we can go with option C as a right answer. Option C is the right answer. If you want, you can check it. Then you will get 17,222 angstrom. Okay. So move on to the next one. Observe this. In a semiconducting material, 1/5 of the total current is carried by the holes. 1/5 of the total current is carried by the holes, and the remaining is carried by the electrons. The drift speed of the electrons is twice. Twice that of the holes. Here, drift speed of the electrons is equals to 2 times the drift speed of a holes. At this temperature, the ratio between the number density of the electrons to that of number density of holes we have to calculate. Okay, so how can we proceed this here? How can we proceed this? So and they have mentioned clearly 1 by 5th of total current, 1 by 5th of total current is carried by the hole. That means current due to holes is equals to 1 by 5th of the total current, 1 by 5th of the total current. So what is the remaining current here? Remaining current is due to electrons. Therefore, it must be equals to 4 by 5 times I, 4 by 5 times I. And we know that current is equals to NEA into VD, NEA into VD. And one more thing, the charge of the electron will be equal to charge of the hole. Charge of the electron will be equal to charge of the hole. Therefore, we can say that drift velocity is directly proportional to I. Okay, they are asking electron concentration. Now we can say uh, electron concentration N is directly proportional to I and inversely proportional to drift velocity. Therefore, we can say that NE by NH is equals to, we can say IE by IH into VH divided by VE. So just substitute all the values here. IE is 4 by 5 divided by 1 by 5. It is equals to 4 by 1 into, what is the velocity of the hole? They have given velocity of the hole where velocity of the electron is, we can say 1 by 2, 1 by 2. Therefore, it must be equals to 2:1 ratio, 2:1 ratio. Okay. Therefore, we can select option D as the right answer. Observe the questions, how they are framing the questions from this chapter. Semiconductor electronics. Okay, so move on to the next question, move on to the next one. What they are saying to us, please read this. The electrical conductivity of an intrinsic semiconductor at 0 Kelvin, as I said, at 0 Kelvin, semiconductor will act like a, semiconductor will act as a pure semiconductor will act as a insulator, will act as an insulator. Okay, therefore we can say that semiconductor will be having electrical conductivity. Resistivity will go to infinity, but conductivity will become 0. Conductivity will become a 0. Okay, I hope it is clear to you. Now move on to the next one. What they are saying to us, a small impurity is added to germanium to get an n-type semiconductor. Here n-type semiconductor. Okay, what is the impurity? And we have studied that whenever n-type semiconductor is obtained, the impurities added must be a pentavalent impurities. Okay, so like that we can answer to this question here. It is a pentavalent substance. Okay, so like this we have to think and we have to answer this question. Now similarly, let us move on to the next question here. Let's move on to next question. What they have given to you. So acceptor level in p-type semiconductor will be, in p-type semiconductor we have studied that there is a conduction band and there is a valency band. So where exactly the Fermi level will lie? Fermi level will lie very close to valency band, that is nearer to the valency band. That is option D as a right answer. Okay. Similarly, let us understand the next question here. Given that mobility of the electrons in germanium is 0.4 meter square per volt per second. Okay, and electronic charge is 1.6 into 10 to the power of minus 19 coulomb. Then we have to find out the number of donor atoms per meter cube. That means we have to calculate Ne. And conductivity they have given. Conductivity is equals to 500 mho per meter. So how can we do simplification here? We know that sigma is equals to Ne into E into mu E. So just do substitution. So we'll get 500, which is equals to NE. We have to calculate. E is 1.6 into 10 to the power of minus 19 into mu E. What is mu E value? It is 0 0.4. 0.4. So just do simplification here. NE becomes equals to 8 into 10 to the power of 21 here. So whenever we do simplification, you will get 8 into 10 to the power of 21 per meter cube. If you want, you can check the option. If you want, you can check the option. Okay. I hope it is clear to you, students. Otherwise, we can easily do this simple calculations. You can easily do this simple calculations. Okay. So move on to the next one. What they are saying to us: if a small amount of antimony is added to germanium crystal, antimony. What is an antimony here? Antimony is an example of pentavalent impurity here. It is an example of pentavalent impurity. Is it clear? So therefore, whenever we consider the pentavalent impurity added, the pure germanium. Germanium is what? Is example of intrinsic semiconductor. Then it becomes the N-type semiconductor. N-type in the sense there will be large number of free electrons. Therefore, the option C will be the exact answer. Option C will be the right answer. Okay. So similarly, let us understand about the next question, what they are saying to us. Yes, this is an important formula. Based on this formula, many times the questions have been asked. Please look at the board. Pure silicon at 500 Kelvin has equal number of electrons and holes. Whenever there are equal number of electrons and holes, and we can call it as intrinsic charge carriers. So please observe this. Intrinsic charge carriers is equals to 1.5 into 10 to the power of 16. They have given me here. Doping by indium. What is the indium? Indium is an example of a trivalent impurity atom, and they have mentioned clearly increases NH, number of holes. Hole concentration becomes 4.5 into 10 to the power of 22 per meter cube. Then they are asking us to calculate what is NE. What is NE here? NE. And we have to be very clear. Whenever the hole concentration is increased, okay, we should be very clear. It must be a p-type semiconductor. So to answer this question, we have to learn that. See here, Ni square must be equals to Ne into NH. Ni square is equals to Ne into NH. So please check this. So I am giving this problem as a homework. And you must get the answer. That is Ne is equals to 5 into 10 to the power of 9 per meter cube. Okay. So move on to the next one. What they are saying to us: a semiconductor doped with a donor impurity. Donor impurity is nothing but pentavalent impurities. So whenever we dope with pentavalent impurities, then we will get N-type semiconductors. Okay. So similarly, let us understand about the next question. Please read this question, and if you have any confusion, you can ask and you can clarify your doubts here. So I am giving this problem as a homework. Please take this problem as a homework and do it by yourself. Okay. I hope you can do this. I hope you will do this question. Let us move on to the next one. What they are saying to us. Please read this problem here. The barrier potential of a PN junction depends on. What is the barrier potential? Depends on. Observe this: type of a semiconductor material, amount of doping, and temperature. Which of the following is correct here? Which of the following is correct? Okay. So please read this question, answer to this properly, answer to this properly. So barrier potential depends on the type of the semiconducting material, whether it is a germanium material or silicon material. We can say the amount of doping, and also depends on temperature also. Hence we can move on to the option D as the right answer. Option D is the right answer. Okay. Now let us see the next one, what they are saying to us. Please read this question here. In an unbiased PN junction holds diffuse from the P region to N region because of, in an unbiased junction here, in an unbiased junction, why the holes will diffuse from P region to N region. Not only holes, electrons will also diffuse from N region to P region. Is it clear? So ಹಾಗಾಗಿ ನಿಮಗೇನಾಗುತ್ತೆ ನೋಡಿ ಇಲ್ಲಿ, what is the reason for that? As I said, because of concentration, that is the higher hole concentration the P region than that in the N region. Because of the hole concentration, electron concentration, holes will get diffused in the P region and electrons will get diffused from the N region, we can say. So move on to the next one, what they are saying to us. Please read this question here. In forward biasing of the PN junction, what is the exact answer? We can say here, positive terminal of the battery is connected to P side and depletion region becomes thick, they are saying. So in forward bias, we know that width of the depletion region will get decrease. Okay, is connected to N side, they have mentioned here, so it is also wrong. The positive terminal of the battery is connected to N side, that is also wrong. The positive terminal of the battery is connected to P side and the depletion region becomes thin. Is it clear? So hence we can select option D as a right answer. I have informed each and every point. So move on to the next one, what they are saying to us. Please read this. The direction of the electric field in a PN junction diode is. What is the direction of the electric field here in the PN junction? So observe this. This is the P region and this is the N region, we can say. And at the P region there will be the electrons, and near the N region there will be holes, Is it clear? Therefore whenever we observe this, the electric field is directed from N region to P region, that is from N side to P side, Okay. Similarly, let us understand about the next question, what they are saying to us. What accounts for the flow of charge carriers in forward and reverse biasing of a silicon PN diode? Okay, what accounts for the flow of charge carriers in forward and reverse bias here? So please observe this. Drift in both reverse and forward bias? No. In forward bias there will be a diffusion current, and in reverse bias there will be the drift, we can say. Drift in forward bias, that is wrong statement. Drift in reverse bias and diffusion in forward bias. Okay, so diffusion in both, it is wrong. Hence we can select option C as a right answer. Option C is right answer. Okay, I hope you understood this question clearly. Now let us move on to the next question, what they are saying to us. Please read this question carefully. The given circuit has two ideal diodes connected as shown in figure. The current flowing through the resistance R1E. They are asking what is the current flowing through resistance R1. So first of all, whenever there are diodes, as I said, whenever there is a diode in a circuit, it just act like a path for the current. Okay, so observe this. So 10, this is a positive and this is a negative here. Therefore D1, what can you say about the D1 here? D1 is in reverse bias condition. Hence it does not allow the current to flow through it. So we can remove or we can eliminate this branch. Therefore what is the current? So please observe this. The net current will become equals to EMF divided by R equivalent. Therefore, I becomes equals to 10 divided by, what is the resistance here? It is given as 2. Is it clear? So, yes, 10 divided by 2. 10 divided by 2. How much you are getting here? So 10 divided by okay, R1 is there. R1 plus R3. Therefore 2 plus 2 we can say 10 by 4. I becomes equals to 2.5 ampere. Hence we can go with the option A as a right answer. Option A is the right answer. I hope it is clear to you, and this is how we have to solve the problems which includes diodes in the circuits. So observe this. Consider the junction diode as an ideal. What is the advantage of the ideal diode? The forward bias resistance will be equal to 0. Okay. The value of the current flowing through AB is, value of the current flowing through AB is. So observe this. This is a P and this is a N. P is at high potential, N is at low potential. Therefore, what is the current? Current is equals to delta V divided by R. What is delta V value here? 4 minus of minus 6 divided by R. What is R value? 1 into 10 to the power of 3. That is 10 divided by 10 power 3, which is equals to 10 to the power of minus 2 ampere. You will get it now. 10 power minus 2 ampere. Hence, option D is the right answer. Option D is the right answer. Okay. I hope you can do this question here. Now, similarly, let us move on to the next question. Let us move on to the next one. What they have given to us. Please read this question here. What they are saying to us. Look at the board carefully and read the question carefully and analyze the situation. In the given figure, a diode capital D is connected to an external resistance capital R is equals to 100 ohm. Capital R is equals to 100 ohm and EMF 3.5 volt. EMF 3.5 volt. If the barrier potential developed across the diode is 0.5, there is a potential barrier across the diode which is equals to 0.5 volt. Then what is the current in the circuit? Then what is the current in the circuit? Okay. How can we answer this question here carefully? How can we solve this problem here? If the barrier potential developed across the diode is 0.5 volt, the current in the circuit is, so please observe this. The applied potential is 3.5 volt. And in order to send the charge through the diode, it has to overcome the barrier potential of 0.5 volt. Therefore, what is I? I is nothing but delta V divided by R. Delta V is nothing but 3.5 minus 0.5 divided by R is equals to 100. Is it clear? Therefore, I becomes equals to 3 divided by 100, which is nothing but 3 into 10 to the power of minus 2 ampere. 3 into 10 power minus 2 ampere, which is nothing but 30 milliampere. We will get it. Hence, we can choose option C as the right answer. Option C as the right answer. Okay. Let us move on to the next question. What they are saying to us. In a semiconductor diode, the reverse biased current is due to the drift of free electrons and holes caused by So how can we answer this question here? So please think and answer. Please think and answer to this question here. So what is the reason for this? Thermal expansion in semiconductor diode, the reverse biased current is due to drift of free electrons and holes due to we can say thermal expansion only or impurity atoms only. That means we can go with both option A and B. It is due to both thermal expansion, also due to what is that thing? This is a conceptual based question. So see the next one, what they are saying to us. So please read this. One more important model. What is the current flowing through an ideal PN junction diode as shown in the figure? Okay. I hope you can do this problem, and please be careful which diode, whether the diode is in forward bias condition or in reverse bias condition. So see here, and this P and this N. P is at minus 1 volt and N is at we can say minus 3 volt. Therefore, P is at high potential compared to N. Therefore, the diode is in forward bias condition. Diode is in forward bias condition. Hence, we can apply this formula. We can apply this formula. So whenever we do this simplification, we should get the answer as 20 milliampere, 20 milliampere. Okay. I hope you understood this. So similarly, let us see the last question of this chapter. Last question of this chapter. What is that? Find the current in the circuit. Find the current in the circuit. Assume the diodes are ideal. Assume the diodes are ideal. Okay. So please observe this, and the resistance is given to be equals to 2 kilo ohm. 2 kilo ohm. Okay. So please observe this. Observe the circuit diagram here. Find the current capital I in the circuit. Assume both the diodes are ideal. So whenever you observe this is a positive potential, this is a negative potential. Therefore, we can say, let us say this is a D1 and this is a D2. Observe this. P region of diode D1 is connected to positive potential and N is connected to low potential. Therefore, this diode D1 is in reverse bias condition. Hence, it do not conduct the current. So, whatever the current it is coming in the circuit, it will flow through the diode D1. It will flow through the diode D1. Okay. I hope you understood this clear, ma. So observe this question carefully. What is the current? What is the current? I is equals to E divided by capital R. E is 20. R is equals to 2 kilo ohm. Is it clear? Therefore, 10 into 10 to the power of minus 3, which is nothing but 10 milliampere. We will get option C as the right answer. Option C is the right answer. Okay. I hope you understood these questions clearly. So these are all the questions which have been asked in the various entrance examinations and also pre-medical entrance examinations in the thing. I hope you understood this. And my request to everyone is, so please prepare the concepts and learn those concepts and practice the formulas as many times as possible. Okay, then only you will get a confidence at least to read the question and also to understand, to analyze the given question. Okay, if you are not able to understand the question, then how can you apply the appropriate formula? Is it right or not? Therefore, please be calm in the examination and don't take much pressure. Okay, you have to work hard before the examination. Okay, not in the center during examination. Before examination only we have to take some stress or strain, and we have to put some extra effort, and we have to dedicate our time, and we have to prepare ourselves. Okay, and I hope you have understood each and every point, and take one reference book and solve the previous year's NEET papers also. Okay, then you will get a confidence. Happily you can go and you can write the entrance examination. Okay, so with this I am going to end the today's lecture. If you get a chance, we will meet you in some other video. Until then, please keep preparing, don't waste your time. Okay, and all the best for your NEET entrance examinations. Okay, so thank you very much. Bye bye.